I'd just like to introduce him. So Thorsten Zander, I guess many of you know him. Thorsten is recently a professor at University of Brandenburg, and today is going to be talking about neuroadaptive technology based on cognitive probing. Over to you, Thorsten.
Yes, hello. Thank you very much for the introduction, and I'm happy to start this session with the first talk. And I'm going to speak about neuroadaptive technology, so technology that can adapt to the mental state of its user directly, and about the tool of cognitive probing, which allows us to build such technology. With cognitive probing, we can generate user models or adapt user models and make better predictions about the user's intention or the user's mental state by collating mental information to the ongoing context. And in the first part of my talk, I'm going to speak about the way passive brain-computer interfaces evolved over time from implicit control to neuroadaptive technology. And when we speak about neurotechnology, we often have in mind that we speak about that we want to use it in human-computer interaction. And when we go way back to 1951, we see a definition of human-machine interaction by Fitz, who said that we have two entities: the user, the human user, and the machine. And the user, and both of these entities have different skill sets. So the user is capable of higher cognition, of integrating new information, dealing with errors, and the machine, if properly instructed, is capable of doing tasks much quicker with higher accuracy or with more power. So when you think about sitting in a car, when you don't have an autonomously driven car, you can go faster to the area you want to go to, but you still have to steer the car to go there. Another example is this power plant control room, where you see 3 chairs where operators can interact with the system, and then you see a lot of information displayed on the screen. So we put a lot of effort in the last decades to integrate information and visualize them nicely to the operators. But the other way around, when the operator is talking back to the machine, they use a mouse or keyboard. And this mouse has a really low bandwidth, and it's basically the same thing as the XY position indicator introduced by Engelbart in 1964. So it's a little bit sleeker now, it looks a little bit nicer and works probably a little bit better, but the concept is the same thing. And this introduces an asymmetry in communication, in human-computer interaction, and also a communication bottleneck. So we, as users, cannot do the task we're supposed to do. So we should actually monitor the ongoing interaction and lead the machine to do the task. But we are now focused on translating our concepts and ideas or commands to the machine by typing something in or using a mouse. And so this is distracting us from the task, and is limiting the efficiency of an ongoing human-computer interaction. But we might be able to widen that bottleneck by using brain-computer interfaces. And as we're going to speak about that, I will give a brief introduction about this technology. So we have a user interacting with a computer, let's say. Then we record brain activity during this human-computer interaction. We will receive a signal, and then we can interpret that signal by extracting features and classifying different mental states from them, which can be translated into command to the machine, which then will adapt to that command. And this will again change the mental state of the operator, of the user, which is then a closed loop interaction, which is based on brain activity independently from muscular activity. And we already spoke about the passive brain-computer interface, which allows us to assess certain mental states, which already, this information is already in the brain. We don't have to formulate that. When we think about, let's say, cognitive load, then of course I could say, hey, I'm stressed out, but the machine could also deduce from my mental workload that I'm stressed out if it would have access to that. And with the passive brain-computer interface, we can gain that access, but not only to mental workload, but also to different types of emotions, subjective interpretations. That was not what I expected. That was wrong. Or context-related responses like, I'm surprised about seeing that. Or intentions, and much more we already can deduce from EEG recording. So there's 100 years or more than 100 years of EEG research, and we know a lot of correlates in EEG activity to mental states. And this paper was published in 2011, where we introduced the passive brain interfaces to the community, and that led to a change in the definition of brain interfaces, so that these type of interfaces are all part of the brain interface research. So we shift from direct control to implicit control. And with implicit control, I mean that we don't have to focus on translating our commands to the machine. The machine is deducing this information from the ongoing interaction and adapts its state to it, like we've seen before. So if you can depict this direct adaptation like this, you have an event, you see the response, and then you have an adaptation, which might lead to new events. But a smarter way to use this information would be to collect all the information, the specific events and the responses to it, and to correlate it in a user model by taking the context into account. And with that, we can build up a user model and adapt it in the ongoing interaction. And with cognitive probing, a specific tool, we can decide, or the machine can decide on its own to present certain stimuli to us to see how we respond to it. And this is, so it could generate information it needs to improve its own user model. The information that is missing could be discriminated by active learning methods or whatever. But if the machine identifies information that is lacking in its model, then it could just present this information to the operator and then take a look at the automated responses of the brain to these stimuli. So in the last 20 years, 15 years, passive PCI research was mainly focusing on this direct adaptation, but in future we can build up user models by collating information from the context to our mental states with using the tool of cognitive probing. And here, this would then lead to the neurotechnology I'm speaking about. So the technology can adapt automatically to the neural state of its user. Here you see the interaction cycle. So we have a system state like before, then we have a probe stimulus. We see the response in the brain, get a biosignal, relate that to the context, deduce relevant aspects of the user state, which then updates the user model, and that can then adapt the system state, but also lead to new probe stimuli. So this is a concept of neurotechnology based on cognitive probing. To give an example of that, so what are we actually, what can we actually do with that? Is it possible? Does it work out? I would like to speak about a study we published in 2016, already a while ago, which was mainly done by Lawrence Call. He did that in his master thesis and continued the work on this in his PhD, where we showed that we can implicitly control a cursor. So typically we steer a cursor by direct commands, but is it possible to steer a cursor to its goal, to its target, with passive brain interfaces with cognitive probing? And therefore, we asked people to watch a cursor moving on a grid, like you see here. We have a designated target, which is in one of the corners, and the cursor can jump one node further away. And in the first part of the session, we invited people with 64 EEG electrodes to watch that and to interpret the movements. But the cursor was moving with randomly, so each direction had the same probability. So here we have a very simple user model. Each direction of the same has the same probability. And this is how it looked like. So you see the cursor preparing its jump, and then the task of the observing human was to say this was a good movement and probably think for him or herself that this was a bad movement. And as this cursor is moving randomly, it doesn't know that the target is nearby, and this is quite upsetting for the observer, but the observer could interpret each move for themselves. And then we trained a model to identify the responses to these movements and fed these responses back to the cursor. And with an approach of reinforcement learning, the cursor would learn what are the preferred directions of the observing human. So at the beginning of the first run, the cursor would just go randomly because it doesn't have any further information. But after the jump, it could ask the BCI, and here we see one response, which was identified as being a good response, a positive response. So we would increase the probabilities for these directions, which is shown here. And then the cursor would randomly move to, based on this probabilities, to another direction. Let's say it would move to the upper left. And then we would ask the brain again and would see, it would get probably a negative response. Then we would reduce the probabilities for these directions, and so on. And step by step, the cursor would learn that the target is in the upper right corner. So with that, we can identify the directional preferences. So in other words, if the cursor moves somewhere, we could ask the brain and then adapt our user model to see that this was a preferred direction. And so step by step, this user model would be adapted and learn about the directional preferences of the user, which then could inform the cursor furthermore to go to the target. So the next movies, you will see how this worked online. On the left-hand side, you will see the actual grid, where the cursor is moving on the grid. And on the right-hand side, which was not seen by the participants, is the actual user model and how it is adapting over time. So the first jump is bad, as it was interpreted as being bad, and the other one as being good. And step by step, the user model adapts over time. And already after a few jumps, you see that the model is quite sure where the target is, and it could lead the cursor to the target. We also did that on a bigger grid, the 6x6 grid, where the target is again in the upper right corner. And of course, it takes a little bit longer, but this model is adapting quite quickly and informing the cursor. And be aware that these that the operators here were, or the human observers were not aware that they were communicating to the cursor in any way. So they, of course, realized that that the cursor is going more quickly to the target than in the first run, but they didn't know that they would influence them. They had the theory that the target is in the upper right corner more often, and that it's easier for the cursor to get there. But we asked them afterwards, and nobody had the clue that they were in any way communicating to the target. So this was really implicit communication. But we're focusing here on the user model, and here you see how this user model adapts. So on the left-hand side, you see the path, one exemplary path the cursor took. And on the right-hand side in the graph, you see the angles related to the target, and the trials, and the color coding shows us the true positives, true negatives, the false positives and false negatives. And on the y-axis, you see the probabilities for these directions, and you see that the model is evolving quite quickly over time, and that we have some mistakes in the model, of course, because the passive PCI is not working 100% correctly. But in the end, we have a quite clear model about the directional preferences of the user. You see another path, which is a little bit more complicated. It takes a little bit longer, but in the end, we still have a very good model about the directional preferences of the observing human. So with that, we can come to the conclusion. And this is, first of all, we can use passive brain-computer interfaces as a tool to detect changes in certain states of the user in real time. This can be used for neuroadaptive and neurotechnologies. It can be seen as a secondary implicit control loop, which does changes of the state of the machine on the fly. It works out quite well, but it's not really smartly integrating the information. After one classification, the system forgets about the actual information that was used. But with cognitive probing, where we combine these information into a model about the user, and also can ask for new information, we can integrate that into the ongoing interaction. We start with a model which can be probably be generated from big data analysis of behavioral data by statistical inference on this generalized big data sets. But then we are missing the personal momentary information from the user. So how the user at that moment interprets the situation, the ongoing interaction. And this information can be accessed with a passive PCI and then be integrated into the user model. And when the system detects missing information in that user model, it can then integrate probes into the ongoing interaction and then fill the holes in the user model and update it and have a better model in the end. And so with that, I would conclude that with integrating passive BCI synchronous probing into our already existing HCI, even though BCI, like we have heard before, is not 100% reliable, we can over time build up a user model that is allows us to make better assumptions about the user, better predictions about the user's intention, so that the HCI can be more efficient, safer, and be more fun to use. Yeah, this is my perspective on it, and I'm happy to discuss with you further about that. Thanks for your attention.